We're starting Unit 3.2 by talking about geometric sequences. We're going to do a warm-up to remind us about arithmetic sequences that we learned about earlier this year. So Dane and Ethan were asked to write a formula to determine the nth term. As a reminder, nth term right here means any term in the sequence. So like if we wanted to find the 41st term, then that would be F41 or A41 or something like that. So the nth term of the sequence beginning at -5, recall that we call that A1, and then changing each time by adding 3, we call that the common difference. So Dane says that the sequence is arithmetic because the difference between two consecutive terms is 3. Seems good. The function rule is going to be linear, correct, with a rate of change of 3, or common difference of 3. Since the first term is -5, the formula for the nth term is 3n minus 5. So everything seemed good in his explanation. Let's check out this last part. A thing I want you to remember is that you can generate a sequence from an explicit rule or formula like this by plugging in values for n. So if I evaluate Dane's work and put f of 1, that would equal 3 times 1 minus 5, which says that the first term should be -2. f of 2 equals 3 times 2 minus 5, which is 1. But we can see in the actual sequence that it begins at -5, so everything, he's getting the right numbers. He has -2, -1, but he's offset by 1 because he didn't write the formula quite correctly. So let's see what he did incorrectly. For arithmetic, we do f of n equals, then we put a1, which is -5, plus our common difference, which is plus 3, times n minus 1. So what he's written is the simplified explicit formula. So we would simplify this -5 plus 3n minus 3, so we put those two together, we get -8 plus 3n is our simplified formula. So his mistake was that he did the simplified formula, but here he put a1 instead of a0. So yeah, he made a mistake with that. Let's see Ethan. So Ethan's, he would add 3 to the previous term, so it's arithmetic. That's true. To write it in y equals mx plus b, use the common difference of 3, yes. Extend the pattern backwards to find the 0 term. Or we base the formula on term 1 and simplify it into explicit form. So either of those are valid. So the way this is explaining is that we need to go backwards one term to -8, and that gives us our 0 term. So Ethan's work is correct. I actually would prefer if we write the explicit formula and simplify it into simplified explicit, but this kind of shortcut also works as well. So we've talked through that. That's good, and hopefully that helped us remember some of the key features of arithmetic sequences. Let's label those here. So an is what we call the nth term. Recall that that can also be f of n or a sub n. So whether we have a parentheses or a subscript, that means the same thing. Here, a1 means the first term in the sequence, and that can be represented as a sub 1 or f of 1. Same thing. D is our common difference, which, as we saw in the warm-up, it reminded us is basically like a slope of a linear equation. So our common difference is represented as d, and then n minus 1 is the, I'm actually going to change this slightly. I'm going to point this to just n. So n minus 1 is the number of steps that we've gone forward in the sequence. So we'll do that. That's the number of steps. But then let's also put just n here. N is the term number. So that was kind of the mistake that the first person made in the warm-up, was that they just put the term number here, not the number of steps that we've gone from the first term. So yeah, kind of a small nuance there. Okay, so we're going to compare what happens in an arithmetic sequence, which is what we've done before. So this is arithmetic. And then our new thing for today is a geometric sequence. And we're going to compare and contrast these. So we just went through the explicit formula for arithmetic. Let's look at explicit for geometric. It also has an, I'm actually going to do a highlighter here. So we have an here and an here. We have a1 and a1. So we start the same way by looking at where the sequence begins. Then instead of plus d, we have times r. So geometric sequences, the difference from an arithmetic sequence is, instead of adding a number every time, we're multiplying by a number every time. So instead of like plus 3 plus 3 plus 3, we're doing times 3 times 3 times 3. So I think of it personally as like leveling up in our order of operations. So order of operations, remember, is P, E, M, D, A, S, or if you do the other one, it's Gemma. So we're basically taking this addition operation and leveling it up to multiplication. So we went from plus D to times R. Then for the last piece, what color kind of pink? Instead of times n minus 1, we have raised to the n minus 1 power. So this is still the number of steps, just like it was before, but it levels up this multiplication to an exponent. And that's because repeated addition is multiplication, and repeated multiplication is an exponent. So you could think of this, if I wanted the fourth term, as being a1 plus d plus d plus d, because we went 3 steps forward, and we can simplify plus d plus d plus d as 3d. On this side, we would have like a1 times r times r times r. But instead of doing times r 3 times, r times r times r is the same as r to the third power. So we're going from repeated addition in a sequence to repeated multiplication, and it levels up our operations from adding to multiplying and from multiplying to exponent. And then we can simplify this down, So basically there's a simplified version. So we talked about simplified explicit in the warm-up for arithmetic. It's a lot less common that we're going to do a simplified explicit, or like that we're going to simplify this into this for geometric. But the thing we talked about in the warm-up, where you can use this version to generate the sequence, is still valid. So if I had a sequence that said an equals 5 to the, I don't know, n minus 1. Yeah, 5 to the n minus 1. Then I could find a1 by plugging in 1 here. 1 minus 1 is 0. 5 to the 0 is 1. Then a2, I would plug in 2. 2 minus 1 is 1. 5 to the 1 is 5. Plug in 3. 3 minus 1 is 2. 5 squared is 25, and so on. So the point here is that you can plug in values to these explicit formulas just like you could for arithmetic sequences. So some reminder vocabulary and a little bit of new vocabulary. A sequence is an ordered pattern or list of numbers. Oh, not pattern. So pattern is at the end here. So an ordered list of numbers that form a pattern. Terms are each item or each number in the sequence. So in the example I just wrote, 1, 5, 25 are the terms, and the term numbers are the position in the sequence. So in the one I just wrote, a 1, 2, 3 are the positions or the term numbers. So term number 1 equals 1, term number 2 equals 5. And also remember, you can write those in a table format. So if I wanted to put these here, I could put n and a of n. So n1 was 1, n2 was 5, n3 was 25, and so on. So very much like what we did for arithmetic, all of these terms are the same, or all of these definitions are the same. For a geometric sequence, it's very similar to arithmetic, but it has a common ratio between terms. So we call it R instead of D. This looks like a multiplying or dividing pattern. If we're dividing, then all we're basically going to think of is we're multiplying by a fraction each time. So the example here goes 1/2, 1, 2, 4, 8. So each one is being multiplied by 2. One that would look like division would be like if I had 48, 16, 16 thirds, 16 ninths, then I'm dividing by 3 every time. So our common ratio instead of divide by 3, we would say the common ratio is 1/3. That's what I'm multiplying by to go from step to step. And then common ratio that we just talked about there is the amount we're multiplying by. So in the first example, it was 2, and in the one I wrote, it was 1/3. All right, so an example, common ratio. We have 4, 8, 16, 32. That's doubling every time, so the common ratio is 2. A1 is 4, A2 is 8, A3 is 16, A4 is 32. Then if we keep extending that, A5 would be 64, A6 would be 128, then A7 would be 256, A8 would be 512, and then A9 would be 1024. So we can just kind of keep multiplying by 2 and extend the pattern. But just like with arithmetic, once we get to numbers that are bigger, so say we wanted to do A25, that would be a very, very, very big number, because these things grow similar to how you dealt with compound interest last year. These grow in what we call an exponential rate. So if I wanted A25, it would be a lot to keep going and multiply, multiply, multiply. So that's where the explicit formula can help to shrink it down. And we would say that this sequence is 4 times our common ratio to the n minus 1. So if I wanted to find A25, I could do 4 times 2 to the 24th power. I don't know what 2 to the 24th power is, so a lot of times if we're not dealing with small term numbers, we end up needing calculators to deal with these because exponential things get so big or so small so quickly. So for small things like A5, A6, A9 even, we can just multiply it by hand, but we don't know exponent multiplication facts like we do for multiplication, so that's where we would often need to bring in a calculator at that point. Let me pull up a calculator real quick. Okay, here's a Desmos calculator. So if I wanted to do A25, then I would resort to using a calculator, and we would do 4 times 2. And then we're most used to using this square button, but this a to the b lets us specify what exponent we want to use. So you can either click that button, or if you prefer keyboard shortcuts, you can type, I thought it was exponent. Never mind. I'm not sure what the keyboard shortcut is. So we can do this button, and now it goes up to the exponent, and we do 24. So we see that that would be 67,108,864. Again, I don't want to do that by hand. I don't want to multiply that out over and over again to get to that number. So this is a spot where if we want to go to big numbers, then calculators become kind of important. But if we're staying with smaller term numbers, then we can do it by hand. Okay, so next example, we have 1/9, 1/3, 139. Now, when there's fractions in there, it can be harder to see what the sequence is doing. So I'm going to look at the whole numbers first and see, okay, this is times 3 times 3. And then say, I'll go backwards and say, is 1/9 to 1/3 times 3? Yeah, it is. And 1/3 to 1 is also times 3. So this is geometric because we have the same common ratio every time. Our common ratio is 3. The fourth term, 1, 2, 3, 4, is given. That's 3. The sixth term would be the next one in the list, so I need to go 1 forward, which would take me to A6 equals 27. The next one is getting smaller, so these are dividing by 2 every time. So we are doing 1/2 as our common ratio. It is geometric, so our common ratio is 1/2. Fourth term is given, that's 6. A6 would be the next term, which is 3 divided by 2. You could call that 1.5 or 1.5, but it's going to be a lot simpler, especially if you need to keep going in the sequence, just to leave that as an improper fraction, 3/2. There's no reason to convert that to a decimal or mixed number. Just leave it as 3/2. Okay, if we know the ratio and the first term, can we list the terms? Absolutely we can. So our first 5 terms, we begin with A1 is 4. Then to find the next term, we apply our common ratio. We multiply by 3, we get 12. We multiply that by 3, we get 36. We multiply that by 3. 3 times 3 is 90, plus 6 times 3 is 18. 90 plus 18 is 108. Then to multiply this by 3, we multiply the 100 And then we look at 8 times 3 would be 24. So we've got our first 5 terms. Beyond that, it would get a little harder to do by hand, but those first 5 are still within reason. Once we start getting into like the thousands, then it becomes a little bit harder. Or like the example I made up where we're in the tens of millions, that one gets pretty tough. Okay, write the first 5 of this one. So we have 80. We divide by 4, so we go down to 20. We divide by 4, we go down to 5. We divide by 4. This is, again, we're going to keep it as just an improper fraction, as 5 over 4, because then when we go to the next term, the numerator stays the same, but the denominator is just going to be times 4 more than that. So if we wanted to keep going, we would just keep multiplying the denominator by 4, and the numerator would just kind of stay what it is, which makes it easier than trying to make decimals or other things like that. Okay, next one, first 5, we start with 6. We're multiplying by 3, so we do 18. 3 times 18 is 54. Now, to do this times 3, we do 5 times 3 is 15, so that's 150, plus 3 times 4 is 12. 150 and 12 is 162. Here, the hundreds place times 3 is going to be, well, I'll just do this one as long multiplication, because I think at 162, we're probably doing that, honestly. So we do 3 times 2 is 6. 3 times 6 is 18. We carry over a 1. 3 times 1 is 3, plus 1 is 486. And you can keep doing it that way. If we needed to go further, we could do 486 times 3. That's 8. Carry that 1. 24 plus 1 is 25, so a 2 comes over here. That's 12 plus 2 is 14, so we get 1458. So you can keep going as long as you're multiplying by reasonable numbers. Like, it's okay. You can keep extending the sequence. It's good practice for multiplication facts. Okay, and for long multiplication. Okay, graph the first 5 terms of the sequence. 1/2 is the first term. So remember that when we graph this, there's no 0 term. So we're starting at 1 on the x-axis, because this is term number 1, and the y value is 1/2. For the second one, term number 2 is 1. That's right here. Term number 3 is 2. That's right here. Term number 4, 1... Term number 4 is 4. That's confusing to my brain for some reason. And term number 5 is 8. Now we can see that if we tried to graph the next term, it would be 16, and that would be right off the graph, like way, not just a little, like way off the graph. So you can see that these dots are rising faster and faster. They're not making a straight line like they would for arithmetic. They're basically approximating what we call an exponential curve, which means they grow faster and faster. Again, this is basically like what you did with compound interest in previous years. So for now, what do you notice? We'll just say that it grows faster each step, and that the graph is a curve. So we'll say curved graph, which later we will call exponential is the shape of it. But for now, we can just say it's a curve to differentiate it from linear, where it's a nice straight line. Okay, now, unfortunately, just like we did for arithmetic, there's 2 ways to write the sequence. We can write it in explicit, which is good, or recursive, which just tells us what the sequence is, but doesn't actually tell us, like, can't tell us values further down the line. So an, we said, was the nth term. We defined these above for arithmetic, but we're going to redo it here. Remember, this is good. So here it says it can also be f of n. So same thing, a, n, or f of n. a1, f of 1, that's our first term. And then r is our common ratio, which is the thing we're multiplying by each time. And n minus 1 is the number of steps that we want to go forward in the sequence. And remember, this one lets us jump forward. In fact, we used it above when we did that 25th step. We were using an explicit formula where we put 24 here because we did 25 minus 1. So the one thing that I want to add here, just like before, is that n is what we call the term number. We kind of have that over here with nth term, but just to say over here, the thing we're plugging in is the term number we want to jump to in the sequence. The recursive definition, on the other hand, does not let us do math, just like it didn't let us do math previously. So an is still the nth term, just like it is on the left side. R is still the common ratio, just like it is on the left side. The one thing that's new or different here is this thing, which is the same as it was in arithmetic sequences. This means the previous term. So this rule is just telling us what the term, it's like telling us how to get a term if you know the one before it. So basically, if we had an equals 5, no, let's not do 5, let's do a simple number like 2. 2 times an minus 1, then that's saying multiply the previous term by 2 to get the new term. But that doesn't tell us what the previous term was. So if I wanted to know a12, then I need to do 2 times a11. So I can't do math with this because I have to know what came before it in the sequence. So the way you could think of it is recursive is what we were doing here. So we were applying a recursive definition to just go one step at a time, step, step, step. That's what recursive can do for us, is just let us move forward by one step by applying the ratio to the previous term. So this is basically moving forward recursively, whereas the one we did up here, this A25, was moving forward using explicit formula, and it let us skip all of those steps from 9 to 25. We didn't have to write them all out one by one. So this problem, we found this part, we went up to number 9 recursively, and then we jumped ahead to number 25 explicitly, or using explicit formula. So maybe the side-by-side there can help you see why they're different and why the pink one is generally not that useful if you want to go further forward in your sequence. Okay, so we're going to write the formula for the nth term of a sequence and then find a8. And we'll do these using the explicit formula because we're writing it. So we're actually going to go ahead and pull in a calculator for these. So we have a1 is 4, and then r is equal to 8 over 4, which is 2. So our explicit formula would be an. And then just like it was for arithmetic, the story of the formula is where we start. So 4 is the start. And the next thing is how we change, which in this case is times 2. So times 2 is how it changes. And then it's always to n minus 1, which is the number of steps that we want to move forward. So for this, we'll do a8 is equal to 4 times 2 to the 8 minus 1. So 2 to the 7th, I don't think we need a calculator for that. Let me just count it. So 2, 4, 8, 16, 32, 64, 128. So that's 4 times 128, which is equal to 512. So we get a8 that way. If we're not confident with our powers of 2, we can check that with our calculator, and we can do 4 times 2 to the 7, and it is 512. Okay, so for the next one, we have 729 is a1. To go from term to term, it might be hard to see with these big numbers. So what I would recommend is skip down to smaller numbers, and here we can say, 27 to 9 is times 1/3. So don't try to figure out the common ratio from like little fractions or big numbers. Figure it out from normal looking numbers. So this one's going to be an equals 729. That's where we start. How we change is times 1/3, and we raise that to the n minus 1 power, which is the number of steps we want to go. So in this case, we'll have 729 times 1/3, and the number of steps is still 7 because we're finding a8 every time. Now this one, I don't want to do, I could do it recursively, right? We're at term number 5. I could just go 3 more steps one by one, but then why did I write this formula, right? So let's use this formula. I don't know what 1/3 to the 7th is, so it's appropriate to use a calculator here. We would do 729 times, I'm going to put parentheses here. I'm actually not even going to put time, I'm just going to put parentheses, 1/3, and then close parentheses to make sure that the exponent is applying to the entire fraction. Then we raise that parentheses to the 7th power, and we get 0.33333. We'd still rather write this as a fraction. So remember that in Desmos, whether you're in graphing or scientific, this little button appears for rational numbers that converts it into a fraction. So I don't want to write 0.33333. I want to say that this is equal to 1/3. So A8 equals 1/3. For this one, we begin at -5. We multiply by 4 at each step. Again, don't look here for that. Look at these small numbers. 5 times 4 is 20, 20 times 4 is 80, and so on. And the sign is staying the same, so we know that it's a positive 4 that we're multiplying by. I'm actually just going to switch to writing parentheses. So -5 times 4 to the n minus 1. And then we can do A8 will be equal to -5 times 4 to the 7th, or the 8 minus 1. So let's go back to Desmos for that one. So we do -5 parentheses 4 raised to the 7 gives us -81,920. Definitely didn't want to do that one by hand. -81,920. So if you need to find big numbers like these, you'll get a calculator. If you need to find small numbers like the ones that we did here, all of these we would expect you to be able to do without a calculator, just by hand, recursively like this. But if we want you to skip further ahead in the sequence using the explicit formula, finding giant numbers or small numbers, then you'll get a calculator for those. Okay, find values in a sequence. So here we have one where we're finding A8, so that's the 8th term, but another one where we're finding n, where the output is 256. So 256 is the term, and we need to find the term number. We know how to do this one, so let's start with that. Our formula is going to be an equals 1/2. We're multiplying by 2 each time, so times 2 to the n minus 1. So A8 will be 1/2 times 2 to the 7, because 8 minus 1 is 7. We're going to use Desmos for both of these, so let's set them both up, and then we'll bring Desmos over. So for this one, we have an equals 1/2 times 2 to the n minus 1. But we know that an is 256 in this case, so we're going to put 256 equals 1/2 times 2 to the n minus 1. Now, to solve this one properly using algebra, you actually need a tool in Algebra 2 called logarithms. Logarithms are the opposite of exponents. They're like an inverse operation, like adding and subtracting or multiplying and dividing, but we haven't learned those yet. So we're going to lean on Desmos for this part. So let's go to Desmos and make this a little bigger, because we're actually going to use the graphing calculator for that second one. So for the first one, we just do 1/2, and then we do parentheses 2 to the 7th. And if you're using your keyboard, you can, instead of using this A to the B, you can do Shift-6, which is like the little caret symbol, the little pointy up arrow. And then you can just type the exponent that way. And then to get out of the exponent, if you needed to put like +2, sometimes it'll just drop you back out, like when you hit plus. Sometimes it won't, so you can use the arrow keys to go back and forth between the exponent and the ground level, or you can use these arrows in Desmos to go back and forth. So anyways, our first answer is 64, but let's go to the second one. So on the second one, instead of knowing what n is, we're going to do 1/2 times 2, but this time we're going to do raised to the x minus 1, so we can actually see the graph. Now notice that it dropped me out of the exponent when I put x minus 1. So it kind of thinks that I want this to be shifted down and do a -1 here, but I actually want it up here to have x minus 1. So in order to do that, I have to put my exponent in parentheses to keep everything up top like that. So we have 1/2 times 2 to the x minus 1 is this curve here. So we could use this graph to find A8. So if we went to where x is 8, we could look at where the graph is, and we would see it's 64. But we can also, and if you want to see that, we can do x equals 8. And there's this gray dot. If I click on either the green or the blue line, I get this gray dot that says 864 is the answer to part A. But for part B, I want to know when the output is 256, or when the y value is 256. So if I put y equals 256, then we have to scroll out some more, and we get this purple line. And I'll zoom back in on the purple line. So where the purple line and the blue line meet, right here, 10, 256, that's going to be the spot, the n value that works for that second one. So we now have our answer to part 1 is 64. So A8 equals 64. And for part 2, we got A10 is equal to 256. So we found that n, or in our case, the graph was x, not n, but that's because it's Desmos. So we found that when x is 10, y is 256. There's also a good chance to remember that whenever we put like A8 equals 64, that represents an ordered pair. That's the same thing as 8, 64 being on that graph. And this one is the same as 10, 256 being on that graph. So this one you should now be able to try based on what we did there. So you write your formula, which is an equals 1/4. We're multiplying by 2 to the n minus 1. So you're going to graph that function. You're going to set y equals 128 on the graph, and then you're going to see where they cross, and that x value will be your answer. Same thing for the next one, and then the next one. What term is the sequence? Is 20? No, this one says what term is 25. So this one, that's a weird way of wording it. This should say what is the term number, or where in the sequence. Let's say where in the sequence, because it's position, right? So where in the sequence is 25. So this one we're looking for a oh no, that's right. We're looking for a y value still. So all of these ones are finding n given the output. So you would do it the same way. We would start off with our starting value, 1600. We're multiplying by half each time, so 1/2 to the n minus 1, or in Desmos, x minus 1. And then we would do y equals 25. So that's how we do all of those. If we are given an input, then we do it the way we did on part 1 here. Okay, so this table is just good practice with applying what we've learned. You write the first term, the common ratio, explicit, recursive, and then explicit in function notation. So we'll write it with subscripts here, and then with function notation over here. So I'm going to leave that for you to fill out and check with the key on Canvas, because that's just good practice for you to do. I guess we can do the first one so you know what it's supposed to look like, and then I'll leave the rest for you to do. So our first term in this sequence we can see is 4. Our common ratio, we're multiplying by 2. Our explicit formula would be an equals our first term, so where we start, then how we change is times 2, and then the number of steps is n minus 1. For recursive, just like for arithmetic, there's 2 parts. So part 1 is a1 equals 4. That's just telling us where to begin. Part 2 says the nth term equals the common ratio, which is 2, times the previous term, which is a sub n minus 1. So this one is where we start, and this one is how we change. And just like with arithmetic, the only 2 parts that matter there is the starting number and the multiplier. We don't actually care about this an minus 1. That's just like telling us that, it's just formatting, basically. Then what matters there is the 4 and the 2. And then function notation here just changes what we did in column 3 to put f of whatever. So f of n equals 4 times 2 to the n minus 1. It's just changing a sub n to f parentheses n, but it means the same thing. So you fill in the other 3 rows on your own and check it with Canvas. Write explicit formulas, we know how to do those. Find the next 3 terms, so you can do that recursively or using Desmos, either way. This one says find A4, you know how to do that. Write a recursive formula. Since we've only done one of those, I'm going to do this one as a like extra. So A1 is equal to 3, and then AN equals the common ratio, which is 4, times A sub n minus 1. Explicit formula you can do, find f of 8. That one you're probably going to do using a calculator, or you can, this one's small enough that you could do it recursively, just doing times 2 times 2 times 2 over and over again. This one, f25, definitely going to use a calculator because we're starting at 7 and multiplying by 3. This number is going to be enormous, so you definitely are going to need a calculator for that one. So that wraps up our notes. Remember to refer back to this page when we get to a quiz and a test to look specifically at this part right here that tells you what all the parts of the explicit formula and recursive definition are. And remember, like, number one thing with sequences, whether it's arithmetic or geometric, is that you cannot do math with the recursive definition. All it does is tell you where you start and how it changes. If you want to find a term using what we did over here in Desmos and plugging things in, you have to change it into explicit, which uses those same 2 values, right? We just take this R and put it over here. We take this, where's the A1? We take A1 and we put it over here. So this is the recursive definition over here should also say A1 equals blank. This is only giving us the recursion rule, not where it begins. So remember for a recursive rule also that there are 2 parts to it, not just one part. It's not just this, it's also where it starts. If you know how a sequence changes but not where it begins, that doesn't tell you what the sequence is. We looked at a bunch of sequences today that have times 2 as their recursion rule or their multiplier, but that doesn't tell us where that sequence started, so it's not fully defined. Okay, that's notes for today.